Let's say you go through some process 1 to 2. I would like to show you how to get started in terms of quantifying the change in entropy, that's a property, from state 1 to state 2. So let's get started with phase change substances first. We'll quickly review the definition of entropy change that we covered in Chapter 5 and then move ahead towards hopefully some things you're a little more familiar with. So in section 6.1.1, let me see if I can move my picture here. Yeah, here we go. Up here in this top right, we're going from state 1 to state 2. And basically all three of those curves represent reversible processes to get from state 1 to state 2. Okay. The book does a good job of talking about how to create cycles, right? You could go process 1 to A to 2 and then come back 2 to C to 1. That would be a cycle. And that helps the textbook author derive ways to quantify the change in entropy for just process going from 1 to 2 along some reversible path. And so I'm going to remind you from Chapter 5 that we said the incremental change in entropy is del Q over T along a reversible path. And if I go backwards a little bit, therefore, we could say capital S2 minus capital S1 would be some type of integral of heat transfer in divided by T along a reversible path. And so for the sketch, we could go along any of these three reversible paths, and we'll get the same numerical result for capital S2 minus capital S1. And so that's an important point that the textbook makes. And I would not be able to do a very good job of this simply regurgitating the textbook material here in video. So I'd like to recommend that you go and you study your textbook to satisfy yourself. Here's how we're going to get some numerical results for calculating capital S2 minus capital S1. Now let's look at the units. Let's look at the units of this fundamental definition of entropy change, D capital S, the incremental change in entropy equals del Q over T. And so if you study that fundamental, you can look at the units, the units of entropy. And so capital S is going to have, well, let's look at the right-hand side. The numerator is going to be joules, and the denominator is going to be degrees K. Similarly, it could be BTUs per degree R. So the extensive property capital S has units joules per degree K and BTUs per degree R. Now remember, so just think about back, and I didn't stretch this out in the slide. Remember that you could have a little q here, but you need to multiply little q by m. So capital Q is m, the mass of a closed system, times little q. And so that's what, if we divide both sides by m, we get d s over m. That would be little s divided by q over m over t. And so the intensive property, and that's what you're going to be looking up. Little s is going to have units kilojoules per kilogram, the numerator, per degree K, and also BTUs per pound mass, degree R, where these temperatures are in the denominator. Now we're moving ahead, and what we want to do is talk about phase change substances. And I want to go back so that you have something that you can start with that you are familiar with. And so I hope that is the PV diagram, the vapor dome. So remember, so you've beat the heck out of this. Pressure on the Y, specific volume, little v on the X. And here's that tried and true vapor dome for phase change substances. And you've got some familiarity with that, right? Well, now we're going to introduce another view, another set of axes, which is going to be temperature on the X, versus specific entropy little s on the x-axis. And it turns out, all I can do is say, it turns out, your textbook does a much better job of explaining this, that you have the same sort of visual look, not exactly the same graphical, but there is a vapor dome associated with temperature and entropy similar to pressure and specific volume. So what I want to do is look at some details about the temperature entropy diagram for a phase change substance. And so it is my hope, we're coming up and I'm going to label these phases. But before we go to the next slide, can you label the phases of the substance, the different phases? What's this phase? What's this phase under the dome? How about if you're laying on this side of the dome, what would that phase be called? What would this phase be called right here, the left-hand side of the dome? And how about if you're to the left of the vapor dome on the PV diagram? In your head, can you immediately identify those phases in words? Well, it turns out that those same phases are going to correspond to the same look on the TS diagram, the same sort of behavior. So you should be able to get this in your head. I have drawn in for a temperature entropy diagram. I've drawn in, this is to scale. I plotted these values of entropy to scale against S and temperature. And notice how it's a little more symmetric. It's not perfectly symmetric, but a little more symmetric. And as a review, I've written down the phases on a TS diagram for a phase change substance. So here we've got superheated vapor to the right of the dome. When we're on the dome, the right-hand side, we're saturated vapor. When we're under the dome, we are a saturated liquid vapor mixture, 2 phases. If we're on the left-hand side of the dome, we're a saturated liquid. And then if we're to the left of the vapor dome, we are a compressed liquid, sort of like tap water, river water. Okay. I've also drawn in 2 lines of constant pressure, and those are called isobars. And you're just going to have to sort of go with me on this and recognize that a line of constant pressure is sort of a dogleg line under the dome because pressure and temperature are dependent variables when you're a saturated mixture. And also I've drawn in 2 pressure lines where P2 line is bigger than P1. So as pressure increases, these lines of constant pressure go up vertically. Very similar to a TV diagram. Lines of constant pressure would look very similar on a TV, specific volume diagram. So I hope you can kind of get comfortable with this makeup before we start putting numbers down on these things. So what's our objective? The objective of this video is to show you how can I get a value of S, of little s, for state 1? How can I get a value of little s for state 2, undergoing some process 1 to 2? And so section 6.2 in your textbook talks about that very thing. So recognize that for phase change substances like H2O, refrigerant, propane, you're going to go to the back of the book and you've got thermodynamic tables there, and you're going to be able to look up values for specific entropy little s. Now, in engineering jargon, and even in your classroom, we instructors, professors, and practicing engineers, we typically call little s, we just call it entropy. And so you're going to have to just sort of get used to that. We call little s just entropy. But in fact, little s is specific entropy. So it's going to have units of kilojoules per kilogram per degree K. All right. And this is going to be retrieving the data from your thermodynamic properties is going to be identical setup as you go for specific volume, specific internal energy, little u, and enthalpy, little h. Same idea. So I think I've got some examples just to illustrate what we're going to do here. Again, remember our objective for this video is how can I get a number for little s at state 1? How can I get a value for little s at state 2. And that way I can determine how the entropy is changed from state 1 to state 2. So I've made some screenshots of hopefully some familiar looking thermodynamic tables for water, H2O. All right. And so remember, entropy is a measure of disorder. So let's study our saturated table. Okay. Now you see all the way to the right, we've got entropy. It just says entropy. Okay. But that is little s. So look, enthalpy, that's little h. Internal energy, that's little u. All right. Complete with units. That shows you the units. Let's look at some numbers for saturated liquid as the temperature increases. Saturated liquid phase as temperature increases. As I look at these numbers, I see the numbers going up. They're increasing some, aren't they? That makes some sense to me. It's that remember that entropy is a measure of disorder. And so can you just use your imagination that as the temperature of saturated liquid water, boiling water, as it gets hotter and hotter and hotter, do you see that the disorder in a sample of that water would get more disordered because of the nature of the temperature? It's kind of a common sense thing. So this makes sense that these numbers are increasing. Now let's say that we have boiled that water away. We've transformed that saturated liquid water into saturated vapor steam at the same temperature. So let's pick 140. So saturated liquid 1.74, saturated vapor, wow, 6.93, a much larger number. Doesn't it make kind of sense to you that the entropy of a saturated vapor at the same temperature would be a bigger number than saturated liquid because it would be more disordered? I've got a more disorderly system if I'm containing vapor than I am in liquid. I hope that helps you get a sort of a common sense feel for these values. Okay, so we talked about the saturation tables, and so mixtures are going to be anything in between. So numerically, saturated mixtures at 140 degrees C will be numerically between these two values. It'll be a saturated mixture. Just like you compute little v and little u and little h under the dome. All right, let's move and look at something similar here for superheated vapor in the superheated vapor phase. Well, sure enough, here we've got little s. So, okay, this is making some sense here. Little s, little h, little u, little v. Okay, complete with units. And so again, we see that I've picked 5 bar. So that is 500 kPa. 500 kPa. And notice we've got different increasing temperatures. Our entropy is increasing. And so that just gives you a little sampler of how would I look up S1 if I knew the pressure and temperature of the superheated vapor phase. How would I look up S2 if I had saturated vapor at 150 degrees C? I just go to saturated vapor and look up this number. Hope that gives you some comfort in the sense that you've already learned how to handle specific volumes, little v, internal energy, little u, enthalpy, little h. And it's going to be the same idea for looking up the property entropy, little s. Now we're moving to ideal gases. So that puts I declare you somewhat experts in looking up little s for phase change substances because of the experience you have already. Let's move on to a TS diagram for ideal gases, a TS diagram for ideal gases. So one thing I want to remind you is for an ideal gas, we don't see a dome. There's no dome, right? It's one phase, the gas phase. And so if you use your imagination, you might think of a dome right around where my cursor is wiggling around. There would be some type of dome over there. But for ideal gases, we're way removed from phase change. All right. So what I've done is I've just drawn a blank set of axes, T and S, but I am showing two lines of constant pressure. And so one thing that does have value is here is a line of constant pressure. And for right now, we can show that, we will be able to show that a line of constant pressure is a line that's swooping upwards in a curve, okay? And also that as you increase pressure, those swooping up curves go up and up and up further and further and further for the same value of entropy. And so that's really the takeaway you want to have on this slide is, so let's see. Looks like I have some examples. It says for T equals constant, entropy increases as the pressure decreases. Okay, so let's look at that. T is constant. That would be a horizontal line. Okay. So let's see, how will entropy change as our pressure decreases? So if we start at P2 and we go along a horizontal line to P1, if we drop our pressure, entropy will increase. Okay, entropy will increase if we drop our pressure. Does that make sense for this concept of increasing entropy means increasing disorder? I think it does. In my mind, if I think about something under high pressure, you've sort of got an ordered substance, but as I decrease the pressure, I can think of the molecules in the system are getting more and more disordered because the pressure's dropping. They're spinning all around and they're more disordered. Let's look at another example. For a constant pressure, entropy increases as temperature increases. So let's imagine that we start here at P1 right here, and we go through some type of constant pressure process up to here. Okay, what's going on here? If we start here at S1 and we go at constant pressure, if we increase the entropy or temperature, we're increasing the temperature. So entropy and temperature are going with each other along a line of constant pressure. Does that make sense? We've got a constant pressure system, but we're starting to heat up. We're adding heat. We're adding heat to the mixture. The temperature's going up. How would that affect the disorder? At least in my mind, I'm thinking, well, that would tend to increase the disorder. For me, these things mentally kind of fall into place. I hope that gives you some ideas on visualizing entropy and relating entropy changes, S2 minus S1, to a TS diagram. And the reason is because you're going to be beating these TS diagrams to death in the rest of the course. So I'm hoping to try to get you comfortable with thinking about the behavior of processes on the TS diagram. Okay, so we have talked about both phase change substances and a little bit about ideal gases. So let's recap. Entropy change, S2 minus S1, is defined in terms of a differential equation along a reversible path from state 1 to state 2. Okay, more on that later. Another reminder is entropy is a property that can be determined by way of tables for phase change substances. I've showed you how to do that, tried to relate it to what you already know how to do. And then we're going to talk about ideal gases in more details in a subsequent video. I hope I've given you some examples of what's coming up relative to the temperature entropy diagram for processes. That's one thing I tried to accomplish. And another was get you thinking about entropy changes, quantifying entropy changes from state 1 to state 2, because that's what Chapter 6 is going to be all about. And your homework assignments are going to be all about that, relating to entropy change. And in some cases, for isentropic processes, let's say that's reversible and adiabatic, there's no entropy change, and that can help you solve problems as well. For an isentropic process, S2 minus S1 equals 0. Hope to see you in the next video.